PPT mode. Yes. I am Dr. R. Raghupati, as I think he has introduced well about me. Anyway, it's a formal introduction about me. I am right now working as Associate Professor in the Department of Computer Science Engineering, Annamalai University. My mail address is csc_raghu@yahoo.com. And you see, I'm going to give a special lecture on image processing using Python. The typical character behind this topic is we all know most of the staff. I think most of you are staff members and research scholars, right? So most likely you may be aware of these topics separately. Maybe image processing separately and Python separately. You might be having a wonderful experience with this. And moreover, the first session is also making you to remember every topics which you have come across with the image processing. I think Dr. T.S. Subhashini Madam has taken the session wonderfully. I think so, right? So hopefully, by assuming that you have some basic knowledge on image processing, and as well as by assuming that you have some idea about the Python programming, based on that, I'm going to start here. Okay. And you can see the package names in the Python. In the first slide itself, I want to introduce all those logos now, right? There is a important package that is called SAIPDLT image. SAIPDLT image is one of the important package for image processing in Python. And apart from that, SciPy is another package. Not only that, there is one more important package called OpenCV. Right, that is a OpenCV package, and apart from that, there is Simple CV also there, and Pillow, Cairo. There are many more packages available. I have just listed out only few top most important packages which are available. Yeah. Any doubt? Any clarification? Yeah. So I'm going to discuss about only few of them. Out of many packages, we are going to take only few of them. The topmost 10 I'm going to discuss about. And the other thing is that what I'm going to discuss in this session especially is first I would like to tell you about the image processing tools in Python. That's what we have seen in the first slide of our presentation. And then a few important concepts on image processing, like image transformations, transforms, then applications of image transforms, then one applications more specifically the image compression technique using DCT that we are going to discuss in this session. And apart from that, there are many morphological operations available, but out of them only we are going to discuss about the dilation and erosion. And segmentation part, I would like to touch some of the one important concept in image processing is the segmentation, in which there is a concept called edge detection, right? That we are going to touch it up. And at last, there is a color model. So every image processing has its own complexity in terms of colors, so that the color model we will discuss how what are the different color models available and how to convert from one to another. And at last, the interesting part of this session is that handling the camera to capture the real-time images and as well as video capturing. That is the important thing, because most of the applications right now are being built by based on the cameras now. Real-time problems they have been taken now. So just I'm going to give an initiation. You are going to continue on your research area to apply all these concepts and get the good application development on your own. Right. This is my idea of my presentation. Let me talk about image processing tools in Python. As I told you, there are so many packages available. Out of them, only top 10 I have taken here. SciPDLT image is the first foremost one. What is that? SciPDLT image is an open source package that works with the NumPy. NumPy is another package which is available for Python. That is a core library actually. That is one of the core library of Python programming. And actually, what it does, it is providing the support for arrays. We know what are arrays available in any language, right? So single dimensional array, two-dimensional array, multi-dimensional array, all these kind of programming on this arrays are all available with NumPy. Like that, there is one more Python package is called SciPy. That is actually scientific model like an NumPy, and what it does, that is going to give that is going to be used for basic image manipulation and processing task. Only basic things are available in SciPy. Right. There is one more package called the pill or pillow. Pill or pillow. Right. What is that? It's a imaging library, Python imaging library. It's a free library for Python programming language that adds supports for opening, manipulating, and saving many different image file formats. We all know there are many image file formats available in our practice, right? Say example BMP, JPG, PGN, PNG. So there are so many TIFF and all they are available, right? So in order to manipulate those kind of images to open them, and as well as if you want to manipulate something on that, and then you want to save that from one image format to another file format, you can make use of this pillow package, and you can do very easily. Right. Then there is another package called OpenCV Python. OpenCV Python is most important. Generally, is OpenCV is the image processing oriented packages and modules are available for C++ also. Right. If you are well versed with the Ubuntu or Linux oriented programming, there you can find OpenCV also. Right. Even in C++ and all is available. Right. Now it's also available in Python, OpenCV. Right. What is that? It's a Python API for open source computer vision library, right? The next, there is a simple CV. The other package name is called a simple CV, right? Open source framework for building computer vision applications. It's an open source framework. Again, all these are just open source. Python is entirely open source, so that we are also going to use all these packages as open source. We need not to spend any money for this. That's the main objective behind this, right? So Makatos is another library, computer vision and image processing library for Python. Likewise, a simple ITK. Simple ITK is another package. It's insight segmentation and registration toolkit. It is a insight segmentation and registration toolkit. And there is one more package is called PG Magic. PG Magic is a wrapper based, actually Python based wrapper for graphics magic library, right? At last, we are going to talk about there is one more package is called PyCairo. PyCairo, right? So it's a set of Python bindings for graphics library Cairo. There is a library called Cairo. For that library Cairo, it is going to be bindings for the graphics library, right? So these are the packages we know, right? What we have to do for doing Python programming, we have to study about the Python packages and what are the functions available inside the packages. This is what we have to understand from these packages. What are the functions have been implemented in these packages. Once you come across all this information from the internet or any documentation, you can make use of these packages for your own applications. This is a major idea behind this. So I have just introduced the package name and its purposes, which is most widely used for image processing, right? Now what we have to do, we have to come across other packages also if you want. So there is a package, there's a website called Python Package Index, PyPI, pypi.org. Okay, that is a website name in which you can find out the package names, and as well as you can find out the commands for installing a package. Say example, if you want to install any package available, if you come across that, if you want to install the package in the Python environment, what we have to do, we have to run a command called pip install, pip space and then install space, then package name we have to give. Okay, then after that we have to give a package name. You see now there is a example here, pip install opencv-python. What it is going to do for you, I told you there is a package called cv2, right? There's a package called cv2 that is available in the package of opencv-python. So I want to install cv2 actually, so that I need to know where it is available. So that I just found it. That's a package called opencv, which implements the cv2. So that I am going to install this opencv-python. It's the name of the package. opencv-python is the name of the package. So what command I am going to use for installing this package? Pip space install space opencv-python. This is what we discussed in the previous slide. Package names and all we have discussed now. So here you can see last one. It's a open source computer vision library. Open source computer vision library. There is a version CV2 is available in this. That CV2 we are going to use of it, right? Yes. Now we know what are the packages available for image processing in Python and how to install those packages, right? Example, pip install opencv-python. Whenever it is required, we have to install the packages. Whenever we want to use of them, we have to install the packages. Once you install the package, we can use these functions available inside the packages in your programming. That we will see with the example in later session. Now you come across the different packages available in Python for doing image processing image processing applications and how to install them. This is what the 2 points we have discussed so far, and where we can find all the packages. You can see all the packages in a website called PyPI, pypi.org, in which you can find all the packages. And if you want to have these installation commands and all, there itself it is available. It's a good website where we can find out all the packages, right? The second part of my presentation is that image transforms. There are so many image transforms available in image processing, but I'm going to handle only 3 of them. First one is called DFT, discrete Fourier transform. Second one is discrete cosine transform, and third one is discrete wavelet transform. Most likely everyone come across all these topics, but let me tell you a few important points on these topics. Right, let me tell you that what is DFT, discrete Fourier transform, is a representation of an image. It's a representation of an image as a sum of complex exponentials of varying magnitudes, frequencies, and phases. It's a very simple definition. What the DFT does actually. What is that? It's a Fourier transform. It's a Fourier transform, right? So that we are going to say it's a Fourier transform is a representation. DFT. DFT is a representation of an image as and how it is going to represent the image as a sum of complex exponentials of varying magnitudes, frequencies, and phases. You see, there is a formula behind this, and then you can able to understand why I have given like that kind of definitions here. Right. You see, there is a capital F of u comma v, in which you can see there is an exponential format in this formula. This is a exponential, sum of exponential, right? Exponential is there, exponential, complex exponential. It's not a normal exponential, it's a complex exponential. You can see minus j here, right? It's a complex exponentials, right? Sum of, what does the definition says? Sum of complex exponentials of varying magnitude and frequencies and phases. You see that varying means summation of 0 to m minus 1, n minus 1. This is a variation, right? Varying magnitude, phases, and frequencies, right? So that way we define the DFT. And similarly, the other definition, the definition for discrete cosine transform is that discrete cosine transform is nothing but it's the representation of an image as sum of sinusoids of varying magnitudes and frequencies. Sinusoids of varying magnitude and frequency. It is an exponential, complex exponential. What is that? Fourier transform is summation of complex exponentials, right? But in the case of DCT, it is a summation of sinusoids of varying magnitudes and frequencies. Summation of complex exponential is DFT. Summation of sinusoids is the DCT. Okay, sinusoids is the DCT. That's how the two things are differing here. Right, it means that in formula you can see it is only based on the cos. This formula is based on the only cos. Cos is available here, but instead of exponential, complex exponential, here you can find out the cos functions. Okay, cos functions here. Okay, this is what the difference between first and second one. Once it once you are able to differentiate these two transforms, you can able to understand what it does now, right? Then third one is the discrete wavelet transform. First one is a summation of complex of exponential. The second one is the summation of sinusoids and third one is what is that? Wavelet analysis, the result of wavelet analysis, right? There will be two components. One is called approximations and another is called details. The one is called approximation and another one is called details. What is this approximations? The approximations are the high scale, low frequency components of the signal. High scale, low frequency component of the signal, whereas details are low scale, high frequency components. That's what we have to understand from this definition. We'll go to the example. There you can see the diagrammatic method and I'm discussing about DWT. You can able to understand what it is exactly. right? Basically, what you have to understand, what is DFT? It's a summation of complex exponentials. What is the DCT? It's a summation of sinusoids. And whereas discrete wavelet transform, there will be two components, approximations and details, right? What is, how these values are computed, that we are going to discuss in a little bit later. And before going into that in depth, we'll discuss about the applications of image transforms. Right. I told you that this topic of FDP itself, you can understand there is a two vast areas, right? Right, like signal processing and image processing, right? In which you can find so many applications based on the image transforms, like filtering, convolution, frequency analysis to power spectrum estimation, and image enhancements, image analysis, image restoration, image compression, video analysis, video restoration, video compression, right? Not only image and video can be replaced by all these terminologies, even you can replace it by signal enhancement, signal analysis, signal restoration, signal compression. Similarly, speech also can be included in this term, speech enhancement, speech analysis, speech restoration. Like these kind of any of these kind of fields can adapt all these terminologies too, right? These are the applications actually. So much of applications are available based on these image transforms like this, in which we are going to talk about only the image compression we are going to talk about, and we will discuss about that in a bit later. Right. Here you see the DFT formula. Right. Why I am going to discuss about this? Whenever we talk about any transform, we need to talk about the inverse transform also. Right. See, there is a two equations available here in whenever we talk about DFT or DCT, whatever it is. Right. So what is this actually? If f of x comma y, small f of x comma y is a function of two discrete spatial variables, x comma y is a function of two discrete spatial variables. Spatial variables are x comma y, right? Then two-dimensional Fourier transform of f of x comma y is given in the relationship. What is that? Capital F of u comma v. What is the Fourier transform? Fourier transform of small f of x comma y. It is a capital F of u comma v. Right? Capital F of u comma v is equal to, what is that? 1 by m by n. What is m and n? Are the size of subimage. Size of subimage. Generally, we take in terms of odd numbers, either 3 by 3, 5 by 5, or 7 by 7, or 9 by 9. Like that we can take. Okay, it's a matrix like. So where the image itself is a matrix almost, right? Once you remove all the header informations, the raw data is nothing but an intensity values, a collection of intensity values on a particular spatial variables, right? With respect to the spatial variables x and y. First value maybe first column, first row and first column. Second value, first row, second column. First row, third column. It is almost equivalent to the matrix. Almost equivalent to the matrix thereafter. So only here it is, whenever we talk about subimage, it is nothing but submatrix. Whenever we talk about image, it is nothing but matrix. Like that, you have to correlate yourself, right? So what is this f of small f of x comma y? It is a value or intensity value. You can say intensity value on the position x comma y. Say x is equal to 2 and y is equal to 3 means that second row, third column, the value available in x in the second row and third column. That is what it is indicated. So like that, we are going to vary the x from 0 to m minus 1. Similarly, y is equal to 0 to n minus 1. First one is row and second is column. Like that you can assume now, right? What is it actually? It's a function of f of x comma y into the intensity value what is available in that position into complex. I told you that it's a complex exponential, right? So e to the power of minus j is nothing but complex exponential into 2 pi within bracket ux by m vy by n. See, the same terminology is available in both form, right? In the inverse transform also, the same thing is available. Only the difference is here it is a minus. In the inverse transform, it is plus. Nothing more than more differences behind this. Ux by m and vy by n. The same thing is available in the power place, right? In the exponential to the power of exponential, right? That is what we have to understand. So what is how we compute the discrete Fourier transform? It is nothing but just a 1 by m into n, number of rows and number of columns of subimage, right? And that loop is, I mean, this is summation means it's we are going to run a loop on that computation. That's the meaning of it actually, right? Anyway, it's a summation of x is equal to 0 to m minus 1, y is equal to 0 to n minus 1 into f of x comma y. Right. What we are doing actually for finding a one value of discrete Fourier transform, we are just running some computation. What computation? For all the values of some images is being multiplied by exponential and it is summed. Exponential of the complex exponentials and is being summed and it is being made as a average. It is being made as a average. That 1 by mn, 1 by mn is nothing but the whole summation divided by m into n, number of elements. That's the meaning of it. So if you take 3 by 3, so there will be 3 by 3 means 9 elements will be there. All individual 9 elements will be multiplied by the complex exponential with some parameters, and then it is going to be summed, and after the result of summation it's going to be divided by 9. So m is equal to 3, n is equal to 3. So what we are doing, just we are making an average of this exponential and it is being assigned to the capital F of u comma v. Like that we compute every values on the new domain. What is the domain actually? What we are doing here, we are converting the intensity domain to frequency domain. What we are doing, the image is represented in the intensity domain, that is being converted into frequency domain. That is what we are doing here. Okay, and then same thing, whenever we apply the forward transform, when we want to get back the original form, means that from intensity to frequency domain we converted. From frequency domain to intensity domain, if you want to convert, then you can use the formula. And the second formula, f of x comma y is equal to small f of x comma y is equal to the same formula. You can find it out. There is no 1 by m into n. You can see that, and only the difference is that capital F u comma v comes inside the summation of summation function, but here small f of x comma y, that is exchanged. That is exchanged here, right? And then in terms of e, there is only sign is replaced. Sign is replaced. Nothing else is there in that. There is no 1 divided by m by n, right? That first term is removed, and one small change in that exponential format. There is no minus sign, and exchanging these two values from frequency domain to intensity domain we are converting, right? So that these two terminologies are changed. This is a formula, and you can understand what we are doing here. We are converting an image in the form of intensity domain into frequency domain. And similarly, once it is converted into frequency domain, we may require to convert them into the frequency, into the intensity domain. For that, we need to apply inverse transform, right? Like, let us talk about how to implement this FFT2. 2 means two-dimensional FFT, right? So what we can do, there are some packages. There are some packages that we have to make use of them. For making use of them, we have to include, or we can say import, right? We can say import. It is equivalent to the import statement in the Java also, right? And import CV2. What is this CV2? It is a package. Where is it available? In computer vision package it is, right? So OpenCV, it is available. So first of all, I have to install that OpenCV, and then I can make use of this. Only one time we have to install, not many times. Only one time we have to install that OpenCV. Inside in it, there is a package called CV2. So now I am going to use import CV2. NumPy. Similarly, there's another package, NumPy. We have talked about all these packages in the first part of our presentation. Right now, there is one more package called matplotlib.pyplot. Right, there are 3 packages we are going to use. Right, I'm going to make a alias for NumPy. I want to make use of that NumPy as NP, a variable, like you can say another name, NumPy. I don't want to use NumPy. Hereafter, I want to use NP. Whenever I say NP, it is nothing but NumPy. In that case, I am going to use NP. Right, I'm going to make use of this NumPy as NP. Similarly, matplotlib.pyplot. It's a very big name, so I want to make the short name of that PLT plot. This is, there is no alias name. As it is, I'm going to use CV2. And second statement, I'm going to use NumPy as NP. Whenever I say NP, that is nothing but NumPy. Similarly, matplotlib.pyplot is nothing but PLT. Here after PLT, which is going to indicate matplotlib.pyplot, right? So first part of this coding is importing required packages. Right? Why it is required? I'm going to make use of these packages for reading of my image. Right? What is the input image? Messy 5.jpg. I told you there are many different formats available. For all these formats, we can make use of these packages for reading. Right? CV2 is supporting that. And what way we are going to read? The grayscale mode we want to read, so that I have passed the parameter 0. Right? It's a JPG image, means it's a color image. I want to read this image as a grayscale values, right? That is why I made it as a 0. Right? What is the function name which I'm using? IMRead. It is almost equivalent to the MATLAB code. Even in MATLAB, you can find it out on IMRead in that. Right? Where this function is available? I told you there is a computer vision library that is called the CV2, right? So CV2.imread, meaning is that package name CV2 in which there is a function called imread. And for that, I am just passing two parameters. First parameter is a file name, and second parameter is in what mode we are going to read them. Right? Simply, I have read this image and I kept it in the img underscore c1. img underscore c1. In that variable name, I am going to have a image, messy image. Right? Now, what I'm going to do, I have to apply fast for Fourier transform FFT2, and then what I'm going to do here to demonstrate how FFT is working, I'm going to shift and then inverse transform of that I'm going to apply. Then I'm going to show all the images in the screen. So my aim is to read the image, applying FFT and shifting that spectrums into the energies into the center, and then decentralize the energy and then inverse transform. Right? Once you apply the inverse transform, you will be getting the same image what you have given in the input. The same image will be obtained. Right? So what we have done, from intensity domain to frequency domain we have shifted, and from frequency domain to intensity domain we are coming back. This is what simply we have done. Right? For that, there is a FFT shift also we applied, and inverse FFT shift also we have to apply, because once you apply FFT shift, we are going to inverse that. Then by seeing the images, we can easily understand what it is now. See the code initially, then we'll go for the output of this code. Then we can easily understand what each steps it does in your coding, right? And then I have to display all these images. For that, I have to make a figure, right? What is that size we have to say? What the size we are going to do? 6.4 into 5. Defaultly, it is 6.4 inches and 4.8 inches. Now I am going to display 5 images, so that I have just given the size of the figure as 6.4 into 5. 5 times I have to increase the size of the figure. Right. Similarly, 4.8 into 5 means that I am going to display 5 images. That's why I have multiplied by 5. I think more than that, right? And then constrained layout is equal to false. Constrained layout, there is no constrained layout. That's what we have said, false. Right, now we come to the important point of the plotting. Right, subplot. I'm going to make subplots in this one. Not only one image. I'm going to make 5 images. I told you. Right. So subplot is the function PLT. What is the PLT? Actually, it's a package. What is that package? Matplotlib.pyplot. Right, now you see PLT.figure of, right, sorry, that is what we have done, and plt dot subplot of 151. What this 151 indicates? There is one row, 5 number of columns. 15 indicates one row, 5 number of columns, in which the first image, the index number, the third number is index number. You can understand now. First value represents the number of rows, second value represents number of columns in it, and third value represent index number of image, in which I am going to say image 1, C1, image C1 I am going to display. What is it actually? It's the original image. Title I have given, I am showing IMShow. IMShow is a function which is going to display the image on your screen. IMRead is a function which reads the input from file. Right? IMRead will read the image from file. IMShow will display the content on the screen. Okay, image on the screen. This is what we have to understand from this basic implementation. And then similarly, I am going to display the spectrum, centered spectrum and decentered spectrum, and then processed image. This is what we are going to display. Same convention. I did not to explain all the things. Only what I have done here, I have made a log of np.log of 1 plus np dot absolute value of image underscore c. It is in frequency domain, right? Once it is in frequency domain, I am just for them I am just making 1 plus that absolute value of frequency domain values, or that I'm going to take a log value. Based on that only I can display. So that I'm going to get a spectrum in my hand, a centered spectrum and decentralized spectrum, and then processed image. Processed image means intensity to frequency we have converted from frequency. From frequency domain to intensity domain we are converting. So what is that first image? 151, 152 means second image. 15 means the first row, 5 columns, third image. 154, first one row, 5 columns, in that fourth image. One row, 5 column in fifth image. So that there will be 5 rows and 5 columns will be there. In one row, 5 images will be displayed. This is the coding. Right. At last, I am going to show the plot. I have created subplots on that. I'm going to show that entirely what we have prepared here, that I'm going to show in the screen now. If you see, actually there should be five images in a single row. For understanding purpose only, I made it like this. Right. In the first screen, I have made only 2 images. Right. Original image and spectrum of that. You can see the spectrums are available at the edges almost. The light colors are available in the almost zero level, and you can see here also in the nearby zero, you can see the spectrums are in the white level spectrums are available here, and the corners of this image you can find the spectrums, right? It's a Messi is a football player, we all know that, right? So this is a Messi player who just kicking the ball in the image, right? For this image we have a spectrum like this. I want to make this spectrum to the center place. That is why I have applied the spectrum, right? Centralized spectrum, I am making it centered spectrum. You see that centered spectrum, you can see a dot, white light color. I mean, white means like a light present inside the image, like you can see. And now around this, more amount of dark, I mean, whiter pixels are available now. Right? This is what centered spectrum. And once you obtain this, we can make you. I mean, we can again getting this spectrum into the decentralized one. At inverse FFT, inverse we have to do like that. We are going to get it in the zero. I mean, again in the corners we will get it. We get the same spectrums in the corners. Now I am going to apply inverse FFT. I am going to apply on this decentralized image. Now again I am getting the same image in my hand. Same image in my hand. You can see that, right? You can see this actually. Now all these 5 images in a single row, it is available. Okay, all these 5 images will be available in the single row, right? Let me execute this program in the Python, right? You all able to see there is a Python in my laptop, right? So the name of the software is called Anaconda, in which I have used the spider option, right? Spider is the editor in which I can able to execute my Python codes, right? So whatever the code we have discussed here, that we are going to execute it here, right? FFT we have discussed, right? FFT only we discussed. So let me check where is this FFT? DFT, yeah, DFTS. DFT. You can see this diagram. I mean, is it audible? I mean, is it visible to you now? My spider, yeah, spider is available now. Yeah. Thank you. There are 4 windows here. You can see like MATLAB or R language. If you are well with the R language, it is a environment like an R or Studio. There you can see there is a coding area, right? Coding area. There you can see the file content in the left top, right? Left bottom you can see console, right? You can see the console. In the right top you can see variables and plots. You can see here all the variables, and then plots we can see in the right top. Similarly, right bottom you can see the help. You can see the files and as well as help directory we can see, and as well as help you can see. This is an IDE where we can easily work with the Python. Okay, so once you can open a file and you can type the coding on this and start executing it, right? There is a run menu here, or you can press F5 for running it. So it's quite easy for us to run with this environment, and then you can see the output of this program. You see, I told you all these 5 images will be in a single row. Now you can see Messi is playing in the first original image is there. The second image is spectrum, and third image is centralized spectrum. Fourth image is decentralized spectrum, and fifth image is processed image. What we have done here, that is available in the plots. Right. What are the variables which I have used here? Like img underscore c1, c2, c3, c4, c5 are the variables which I have used here. Right. Let me see the variable content also here. Variable explorer is available. There you can see what is the size and what is the content of them. That we can see what the type of that variable. All these things can be easily understandable through this IDE. That is why I chosen this IDE for understanding the images, right? So that is what the effect of this spider. Just I use this spider for executing these programs, and you can see all the coding what we have discussed in the slides. You can see this 5 computation we are doing, image reading we have done, and then FFT2 we applied, and then shifting of the spectrum we have done, and then inverse shifting of the spectrum, and after that you can see the inverse FFT we have applied, right? So this is what we have to understand how it can be executed, that I have demonstrated here, right? And if any doubts comes, then we can discuss in the later stage. Now we will go to the second transform, that is called DCT, discrete cosine transform. Let me see the formula behind this is summation of sinusoids I told you, right? Here also 2 different variables we have used, g of u comma v. Instead of capital F of u comma v, I have used here g of u comma v, nothing else, right? The computation is slightly different. What is that? Here the computation involves with the same looping state, the same summation 0 to m minus 1, y is equal to 0 to n minus 1, the same thing. But here alpha of u and alpha of v, there are 2 functions available in this that we are going to compute. How this is being computed? Based on the value of u, the alpha u is computed. Based on the value of v, the alpha v is computed. If u is equal to 0, the alpha u is equal to square root of 1 by m. Very simple, square root of 1 by m. If it is non-zero, then it is a square root of 2 by m. Square root of 2 by m. Right. This is what we have to understand, how the alpha u is computed. If u is equal to 0, the value of alpha of u is equal to square root of 1 by m. If not u is not equal to 0, then ultimately it is from 1 to m minus 1. Right. In that case, it is square root of 2 by m. Similarly, alpha of v. Alpha of v is nothing but if v is equal to 0, square root of 1 by n. It is not m, it is n. Right. U is dependent on capital M. V is dependent on capital N. Very simple. The same formula we can able to understand this. So let me go to the next component of this equation, cos. Cos of 2x plus 1 into u pi. 2x plus 1 into u pi divided by 2m. Similarly, cos of 2y plus 1 into v pi divided by 2n, where all these values generally varying from 0 to m minus 1 and 0 to n minus 1. Where what u comma v, right? U comma v will also vary from 0 to m minus 1 and 0 to n minus 1. This is how the DCT is working now, right? And similarly, we have to discuss about the inversion of this. It is inverse DCT. Actually, the DCT, FFT are invertible transform generally, right? So here also we can see there is an inverse transform in which all the components are same, only just exchanging the value of f of x into u of v, g of u comma v. Nothing is there, nothing different between the first equation and second equation. Only the difference is instead of f of x comma y, we replace it by g of u comma v, where this alpha of u and alpha of v were outside the summation. Now it is inside the summation. There is no other changes in this equation. You try to see, compare this, and you can able to understand what is the inverse formula is all about. DCT, there is a basis function. There's a DCT basis function. Actually, it is nothing but it's a component which is present inside the equation. You can see the common terminologies between all. You can see alpha of u, alpha v, and cos of 2x plus 1 into u pi divided by 2m. Similarly, cos of u 2y plus 1 into v pi divided by 2m. This is altogether except the image value, except the intensity value. The rest of the things is going to formulate the basis function. This is what basis function is all about, right? Where b of u comma v, the basis function b of u comma v is defined as alpha of u into alpha of v into cos of 2x plus 1 into u pi divided by 2m, cos of 2y plus 1 into v pi by 2m. You can see this is the basic function. Right? How it is going to be computed? By varying the value between 0 to m minus 1 for u and x. Similarly, by varying the values of v and y between 0 to n minus 1. By that way, we are going to compute it. You can see this diagram and you can easily understand what we are going to do with this basis function. It is nothing but a matrix, computation of matrix, right? What we are going to do? By varying the u and v from 0 to m minus 1 and n minus 1, we are going to do. Say if n is equal to 3, m and n is equal to 4, not 3, 4, then how it is going to be computed? U will take the value from 0 to 3, and similarly v will take the value from 0 to 4, 0 to 3. Right? What we are going to find it out here, you can see when we vary the v horizontal frequencies, we are getting it. When we varying the u, we are getting the vertical, horizontal frequencies, variation in horizontal frequencies that we can see it in the v. Variation in the vertical frequencies that we can see in u by varying the u. Right? You can see the when we vary both, we are getting the vertical frequency variation and as well as the horizontal frequency variations in this portion, the last portion of this. So how many matrix we are getting it here? 4 by 4 means 16 matrices we are going to get it, right? So by straight away multiplying the sub images, we can able to find out the values on that. So this is what we have to understand. When you have u comma v is equal to 0, there is no much differences in that. There is no frequencies. I mean, it's a highly energized pixel available here. And when we varying the u and v, you can see horizontal variation and vertical variations in it. Right. So what is going to happen when we multiply two matrices? The result of the DCT function, what we will have in the top corner, we will have highly energized values. Highly energy values are available in the top corner, top portion. That is why you can see this top portion of the 0, 0 and variations in the horizontal direction and variation in the vertical direction. Only by keeping these values, we can able to reconstruct the image. Other things is not much important. That is how the image compression is achieved actually, right? That we will discuss when we are discussing about the image compression. Right, come to the point here. I'm going to implement this DCT. Right. For that, what are the packages available? I'm just looking at the documentations and found that there is a SAIPDLT package. SAIPDLT package. SK image. SK image is another package. Apart from the previous packages, 2 more packages I'm going to use here. Right. So SAIPDLT, another one is called SK image. The 2 packages I'm going to use. From that, I'm going to use only DCT, IDCT from them. Right, import only the IM read from the SAI image. Import only RGB to gray. Only these functions I'm going to import here. IM read is a function, DCT is a function, IDCT is another function, and similarly RGB to gray is a functions which I am going to use it from SciPy.fft pack. Right, that package. In that package, I'm going to import only the functions DCT and IDCT. Right, another one IM read and similarly RGB to gray functions. Right, based on the single dimensional DCT, I am going to implement 2-dimensional DCT. I have my own definition for DCT2. That what it does actually, DCT of A transpose comma normal orthogonal comma dot transpose comma normal orthogonal. Okay, normalization is nothing but orthogonal normalization. Right. So this is what the basic implementation of DCT2. It's an inner call, right? DCT dot DCT. Very simple. IDCT of IDCT. So that way we have implemented these two the two-dimensional version of DCT, right? Very simple. This is implemented by our own. What we have done, we have used the single-dimensional DCT function available in the SAIPDLT, right? The next, yeah. Once I read the same messy image, I have to convert that into the gray. Earlier we used the IM read with the zero calling, right? With the zero calling, right? There was two parameters in that function. IM read image file name, comma 0 we have given. But instead of that, I want to use the another function called RGB to gray. So once you read the function, read the file, it is going to give you the RGB values, right? RGB means red, green, blue format, right? Then next, I'm going to convert that into gray. There is a function called RGB to gray function that I'm going to use it on the IM read. Right. Once it is read and it is being converted into grayscale, that is going to store it in the IMG value. A variable name called IMG will keep the gray value of messy image. Right. Now I'm going to apply DCT2 on that image. Whole image I'm applying. Right. Whole image I'm going to apply inverse DCT also. Right. That applied forward DCT. The FDCT means it is forward DCT. Image forward DCT. Right. After applying that, I'm just stored it in the IMG forward DCT. IMG IDCT means inverse DCT. Once apply that, I am just going to store it in the IMG IDCT. Then there is a function called all close. All close is another function that is going to tell you whether two images are same or not. Two images are same or not. NP is nothing but numpy, right? Now NP dot all close of function, right? All close is the function name. Within that, I'm going to say IMG comma IMG IDCT, right? IMG and IDCT. Okay, reconstructed image and the original image are same or not. I want to check it out. Right, reconstructed image and as well as the original image are same or not. If it is same, it is going to return true. Otherwise, it's going to return false. Right. That's a major thing is about the all close. Then similar to the first exercise, here also we are going to have only 3 images, but I'm going to use the same space. But that same space allocated for the figure is 6.4 by 5 into 5 times I'm making it. So out of them, only some gap may be there between one image to another image. That in that way I'm going to manipulate here, right? In which what I'm going to do, first image I'm going to display the original image, and second image I'm not going to use. Third image I'm going to use 153. You can see 153 here. In the third index, I'm going to use the image forward DCT that I'm going to show, and then fourth image I'm not going to use. Image I'm going to use inverse DCT. Right. This is what my objective, and the same. It is almost similar to the previous exercise. That is why I'm just passing on this discussion here. If you are, you can easily understand all these codings, right? And that is why I'm just moving on to that. And similarly, here you can see there are 3 images constructed here. One is the original image, the DCT coefficients you can see here, and then reconstructed image. Right, all of them in a single row. All of them in a single row. There you can see there is a gap between the original image and the DCT coefficients, and as well as DCT coefficients to reconstructed image. Why? Because I have not used the second image and fourth image. Right, that is why we are having a gap in between them. Right, let me execute this program, and then you can able to understand how the effect of DCT now. Right, DCT function is here. Now I am going to execute it. You can see messy image. There is no second image. There is no fourth image. There is a DCT coefficients and as well as the reconstructed image. Now to make it more clear, we have presented in the PPT. Nothing more than that. All the codes and which are available here is already discussed with the PPT. Right. So now we can go to the next slide. DWT. DWT. Right. I told you what is DWT. There will be it's a wavelet. After the analysis, we will have 2 components. One is called the what is that? One is called the approximation and as well as details. Okay, approximation and as well as details. So there are 2 components we can get it out of this analysis. Here I have given 2-level processing. 2-dimensional means I'm just going to have a 2-level processing here. Right. What I have done in first level, for every rows I'm going to apply in the first level Second level, I'm going to apply it for every columns. Right. What is done here? After what is done here, I'm going to apply two filters. One is called a low frequency, low pass filter. Right. It means that low pass filter. Low pass filter LOD. It is not denoted as LOD, and high pass filter HID. In the diagram, you can see there is a filters. Two filters. There are two pass filters we have used. One is low pass filter and high pass filter. First level, you can see there is a low pass filter which is being applied for rows, and high pass filter applied for rows. Right here, there is a down sampling is done. Down sampling is done to down arrow 1. Down sampling is done here. What it does, it keeps the even indexed numbers. It keeps the even indexed columns. Even indexed columns. 2 arrow down arrow 1 means it is also down sampling, right? What it does actually, for every 2 values, it's going to keep only 1 value. Means for every 2 columns, for every even indexed means 0 column, second column, fourth column, sixth column, eighth column. For them only we are going to have the value. For the odd number of columns, we are not going to keep it. Only the even number of columns we are going to keep it. That's the meaning of it. Right. And then similarly, after applying this low pass filter and high pass filter, you will get 2 components out of this. Right. Here we are going to apply it for, again we will apply the low pass filter and high pass filter. Right. High pass filters output of that, we are going to apply low pass filter and high pass filter. Now you are going to apply the down sampling again. What this down sampling will do, it will keep only the even indexed rows. Row wise it's going to keep. Row wise it's going to keep. Even indexed means 0 to 0th row, second row, fourth row, sixth row, eighth row. Like that it's going to keep it. So that you can see the output of low pass filter and low pass filter is called as approximation. The output of low pass filter and low pass filter, 2 low pass filters, output of these 2 low pass filters is called approximation. The rest of them is going to be called as coefficient, detail coefficients, details. What detail it is? First one is horizontal detail. What is that horizontal detail? Low pass and high pass. LH. You can see LH. Now I can say you that subbands which is produced after applying 2 pass filters, right? Low pass LL filters applied, and I'm getting a approximation. LH is applied. L means low pass and H means high pass. Both is applied, and the output of that is called a horizontal detail. The output of LH is called a horizontal details. Similarly, HL is called a vertical detail. HL is going to be called as vertical detail, and HH is going to be called as diagonal features, diagonal details, right? There are 3 details available here: horizontal detail, vertical detail, and diagonal detail. It can be represented in easier manner. LL is nothing but approximation. LH is nothing but horizontal. HL is nothing but vertical. HH is nothing but diagonal. That way we are going to get the output subbands. We are going to get it in our hand. Now we want to implement this concept in our Python. So what I'm going to do, I'm going to use a NumPy. This is already known. These first two packages are known to you. Now I'm going to use a new package called PyWT. PyWT. There are 2 things I'm going to do: PyWT and data. Why this data is required? The common image formats are available in that. So one of the famous image is cameraman in the image processing. That the data is available in PyWT package itself. So that I'm going to make use of that. So original is equal to, in the earlier example, we read input from file, but it is available in the package itself now. So I'm going to make use of that image by calling camera function. Means that the cameraman is the image that will be loaded in the original variable. And what I'm going to do, I'm going to find out approximation, horizontal, vertical, and diagonal details. So that I want to display titles on that, so that I have initialized the values for the titles. And coefficients, I told you, LL, LH, HL, and HH is equal to coefficients of 2. And once I applied the DWT2 on this input image, then I will get 4 components on that. What are the 4 components? LL, LH, HL, HH. LL is nothing but approximation. The rest of them is going to be called as details. Right. I'm going to display all these values in the screen to understand what it is. Right. In the looping statement, I made it here for making all the things in a single looping. Right. I can able to find out the image in the continuous manner. Right. Subplots I'm going to add. It's another method of doing displaying. Just you can able to understand this. Tight underscore layout and then plot dot show. Figure we have created and then we have just showing into the screen. Nothing else. A similar kind of syntax that you can easily understand. I don't want to waste much time on this implementation details. Right now you can see that approximation almost like an image, almost like a image. What is that approximation? L, low pass, two filters applied on the same subband, and the row wise and column wise we applied, right? And we got the approximation, right? We got the approximation. LH horizontal detail. LH is horizontal detail. You see horizontal edges, you can find it out here. You can find out the horizontal edges. Here you can see vertical edges clearly in the third image. Vertical details, you can find it out. The image, the edges available in the image, vertical diagonal detail. Diagonal details means in both direction. The edges available in both direction, you can able to find it out in the third one. So this is what we get it after doing the DWT. Approximation, horizontal detail, vertical detail, diagonal detail. We don't require these details. Only the approximation itself is enough to reconstruct the original image. So that it is enough to keep only the approximation, need not to have the details, so that you can reduce the size of information which is required to represent an image. This is how the DWT is working on behind. Right. Now I'm going to demonstrate this DWT also. If you want, you can execute it. Okay. The same thing. Let me go to the next topic now. Image compression using DCT. Image compression using DCT. I told you all these transforms main application is one of the main applications is image compression. Right, there are so many applications available which we are going to discuss only image compression, not other topics here. Right, what is the image compression? I told you that the image compression is a process of reducing the amount of data required to represent a given quality of information. Right, given quality of information. I have given 10 values to you. Right, you are representing it with 10 values. If somebody is representing with the 5 values of the same information, that is called compression. It's, for example, if you take an image, right, there are 100 pixels are available, means 10 by 10, right, 10 by 10, right. If you want to represent an image with 10 by 10, this is one method. The another one is representing the same 10 by 10 with the 5 by 5 values, with the 5 by 5 value. He is doing some manipulation, some manipulations or some processing is done. After that, he is going to show that. Okay, so only he required only 5 values, 5 by 5 values. The other one requires 10 by 10 values. What is happening here? The compression is done in the second form. Right, only 5 by 5 values. 5 by 5 means 25 values. Only 25 values enough to say 100 values. That's the meaning of it. So that is called compression. Right. What is that compression? There are two types of compression. Right. One is called a lossy compression. The another one is called a lossless compression. What is the meaning of lossy and lossless? Lossless means once you reconstruct the original image, there is no difference at all. No difference at all between original and the reconstructed one. There is no difference between original and reconstructed one. That is the meaning of lossless. Lossy. Lossy means there may be slight deviation. Maybe instead of 250 value, 251 may be there, or 249 may be there, 48 may be there, right? Maybe small deviation. But what is happening here? The naked eye, we cannot able to see what's the difference between the original image and the new image. So what can be done in this case? There is a parameter, there's a metric called peak signal to noise ratio. Peak signal to noise ratio. You just compute the peak signal to noise ratio. If that decibel value, the result of that is a decibel represented in the decibel. If that value is more than 25, you cannot able to see the difference between original image and the reconstructed images. You cannot able to see in the naked eye. But this PSNR value will give you the good idea about how much it is deviated. Right? If it is lesser value, it is more deviated. It is lesser value, then it is more deviated. It is more than 30 decibel, it is not always good. But sometimes you may get 50 around for many good values, right? Right. So if you give same images, it is infinite almost, right? So you can see maximum value, right? So more, I mean, means that if you have higher values, it means more same, almost same. That's the meaning of it, right? So peak signal to noise ratio that we will discuss in the next few slides. The formula behind that and all we will discuss. And next, come to the compression ratio. What is compression ratio? I told you, for indicating same information, you need n1 bytes. The other one needs n2 bytes, right? Actually, n2 byte is the first, original size, and we need only n1 bytes for representing it. It means that that is a compression ratio, n1 by n2. Right? N1 by n2. What is that? N1 and n2 represent the number of information carrying units in two data sets that represent the same information. I told you only 25 pixels are required for representing it. The other one required, the original required 100 pixels, 25 by 100. Right? That is a compression ratio. That is a compression ratio now. Right. Now I am going to apply the DCT for this. Right. Now I am going to apply the DCT for it. All the packages is well known to all of us now. CV2 package, NumPy package, Matplotlib. So package is not required for us. There is no problem at all for understanding the packages. And input also, we know how to read the input. There is a function called imread. I am going to CV2 function so that file name comma 0 I have supplied here. And after reading it, I have to convert that to float value. The values are in uint actually, uint 8, unsigned integer 8 actually. From that, I have to convert it into float type for manipulating it. Right. So then after converting it into the floating value, then I'm applying the DCT. I am applying the DCT available in CV2, two-dimensional DCT it is. Right. I have just applied the DCT on CV2, and I'm going to make the image to display, so that I'm just applying the log value on absolute value of image and the resultant image. And then I'm going to apply the inverse DCT on the result obtained here. Image underscore DCT. Image underscore DCT is the result of our applying the DCT, so that we are going to get the original image. Right now, you see, I'm going to use only the top portion of that image. As I told you, not all the images is required, all values in the image is required. Only the top portion I'm going to take it out of them. Why I'm going to take only top portion? Because once you apply the DCT, highly energized pixels are going to be available in top portion. I told you that basis function, you can see all the variations are available in the first row and first column itself almost. So only that portion is enough for me, right? Only the top portion is enough for me to reconstruct the original image, right? The rest of the image values are going to be 0. I'm going to take only out of this picture size, size maybe more than 200 something, right? I'm going to take only the top portion of that. What is that? 0 to 100 rows, 0 to 100 columns I'm going to take. Right? Only that I'm going to take out of this process to one, and the rest of the values will be, for this image will be 0. So, right? By adding the 0 for the rest of the images, the rest of the pixels, I'm going to construct the second reconstructed image, right? So now I'm going to reconstruct the image based on the record temp2, recover temp2, right? Recovery temp2 is a variable name in which the top portion of the image is going to be the value which we got after applying the DCT. Then rest of the images is going to be 0 only the zeros. Right now, I'm going to apply inverse DCT on this value, and I'm going to get the compressed, recovery from the compressed image. Now I just manipulated it, and you can see all these commands and all known to you. Just first one is the original image, second is a DCT transformed, IDCT transformed, and decompressed image. Now you see that the Lena image I have taken as an example here, original image. After that, we applied the DCT. Then immediately with this value, I have applied an inverse DCT. Okay, so there is no difference between original and inverse DCT. Now I have taken only the top portion of this DCT, 100 by 100 only I have taken from this DCT transformed value, right? Not all the values, only the top portion of this DCT. After applying the DCT, the top portion of this we have taken, and with this, the rest of the values were made it as a 0, and we reconstruct the original image, and that is called a decompressed image. After the compression, we make the manipulation to get all the original values again, right? This is what the compression is all about. See, only the top portion 100 by 100 is enough for me, not the rest of the values. What I have made, assumed that all of them are 0. I assumed that all of them are 0. What happens here? There is a slight deviation between original and decompressed image. Can you able to identify with this naked eye? No, it's not possible, because once you apply inverse DCT, almost similar, not exactly same. So why it is? Because it is a lossy compression. DCT is a lossy compression. As because of lossy compression, DCT will produce the slightly varied image. Say for example, one pixel available in the Lena image, original image, is 250. The same pixel here in the reconstruction, it may not be same 250, maybe 251, or sometimes maybe 250, sometimes it may be 249, or sometimes it is 247, anything in between that, right? Anything in between that, so that a slight difference will come. So that it is there is a slight differences, right? Now you see how I can able to see. As I told you that it cannot be viewed by a naked eye. So how can I measure it? There is a formula for this. It is nothing but difference between original and reconstructed images, and make the square of that, and make all the pixels value summation, and make it average. That is called mean square error. Error means what is error? Difference between original and reconstructed. That is the error. Mean square. Make the square on. After making the square, make the mean of that, average, taking the average of that. So take the difference between each pixels and make the square, and divided by m by n. It's nothing but making a mean. So after that, if you take a root of that, a root means square error. If you make a square root of this, that is called RMSE. So what is that RMSE? This formula can be rewritten. The PSNR formula can be rewritten as 10 log 10 into L minus 1, the largest value minus 1 into whole square divided by MSE is there. Once you make the square root of this, that MSE will become RMSE. Right? What is happening in the square? The square is removed because it is a square root. So square will be removed. Only L minus 1 will be there. What's the largest value here? 0 to 255. So 255 is the largest value. So 255 minus 1 divided by square root if you take, that is called RMSE. Square root of this MSE is nothing but root means square error. So that it's going to be a square. So once you make the square, this 2 will come in front of it. So that 20 log 10. This is a formula for PSNR. PSNR is equal to either this formula we can use, or the second one we can use. For our implementation, we can use the second formula, 20 log 10 into L minus 1 divided by RMSE. What is RMSE? Root means square. Compute the value and take one square root of it. Right? That is RMSE. So RMSE is a square root of MSE. Very simple. Square root of MSE. Right. Now, by computing the PSNR value, it is actually represented in terms of decibel. So by computing that, we can able to understand how it is different, how it is same. Like that, we can able to understand. Okay. Now we'll go to the morphological operations. There are so many morphological operations available. Out of them, we are going to discuss only few: dilation and erosion. Right? What is the dilation? Dilation adds pixels to the boundaries of objects in an image. Only it is going to add the pixels in the boundaries. What is erosion? It removes the pixels from the object. This is what the difference between erosion and dilation. There are few more like open, close, and all is available that we are not going to take care now. Right? What is dilation in binary image and in the normal image? If it is a binary image, what the dilation does actually, it is going to find out the neighborhood pixels. If any one of the neighborhood pixel is 1, the result is equal to 1. The output pixel is a 1. Similarly, in the erosion, if any one of the neighbor pixel is 0, the output is 0. Erosion is going to remove a pixel from the boundary, and the dilation will add a pixel to the boundary, so that the 1 will be computed like that. And if it is not the binary image, then what is going to do? The maximum value in the neighborhood, here the minimum value in the neighborhood, nothing else. We know what is the neighborhood concept. The pixels around the current pixel. Maybe one pixel before that in the same row, next to that same row, and before first column, same pixel, same column, previous row, same column, next row. Like that, 4 neighborhood concept we can take. 8 neighborhood concept also can take. Right? It doesn't matter either you are using 4 neighborhood or the 8 neighborhood. Based on that, the result may get vary. Right? Surrounding pixels is being considered as a neighborhood. Out of them, if any one of the pixel is 1, the result is 1 in case of dilation. In case of erosion, any one of the pixel is 0, the result is 0. On the other hand, if it is not a binary image, the maximum value surrounded by the pixel will be taken for the current pixel. The minimum value for the surrounding pixel will be taken for the erosion. That is what the difference is all about. You can see the difference. Just you load the image. We know how to load the images. And after loading the images, what we are going to do, we are going to apply a kernel function, right? That kernel function is going to have all ones. That applying the all ones to the erode and dilation function, right? All ones with the 5 by 5 submatrix, we are going to make it. Right? Erode and dilate is the function name which is available in the CV2 itself. But applying that, we are going to get it in the two variables, erosion and dilation is a variable name. So the images are available: image, erosion, dilation. All the things are going to be displayed on the screen. Based on our discussion, you can easily understand this coding now. So you see the difference between image, original image, and the eroded image and dilated image. You can see the thickness of the J is reduced here, right? So it just means eroded, right? And dilated means the thickness of this J will be getting increased because the boundary will be increasing. The pixels in the boundary will get increased in the dilated. So that you can see the difference between morphological operations on these things. Right. Next one is that image segmentation. What is the segmentation? The segmentation is nothing but subdivides an image into its constituent regions of or objects. You can say, right? Constituent regions or objects. This image directions can be done with many operators like Sobel, pivot, or many operations are there. Many operators are available. One of the famous is Sobel, right? So how the operator is going to work behind this finding the edge direction? We will compute a result of a summation of Wi into Zi. What is Wi? Wi is nothing but mask coefficient. And what is Zi? The gray level pixel value, right? The gray level pixel value associated, right? That is what the Zi is all about. So multiply the mask value and the pixel value and make it summation. That is the result. Right, like that we have to move across all the mask from one pixel to all the pixels. So by that way we can able to find out the edges. Right, what is the Sobel operator for horizontal image? I mean horizontal edges, we are going to use the first matrix. For vertical images, we are going to use the second matrix. What is that? -1, -2, -1 in the row, 0, 0, 0, 1, 2, 1. This is a Sobel operator. Like this pivot operator, the other operators are varying in these numbers. Right. We'll go to the example, how to write the code for it. Right. These packages is known to you. I have initialized the array -1, 0, 1. -1, 0, 1 is the first row. -2, 0, 2 is the second row. Third row, -1, 0, 1. It means the second array I have initialized here, and I am applying the vertical image. I'm going to find out the vertical image. So I am just making image, comma -1, comma filter. What I have given here as a filter, that is a second one, vertical filter I have applied. And then second one, I have to transform that filter dot transform. T is applied here, and you can get the other output here. Right. Once you read the image, apply the vertical filter, apply the horizontal filter, and show the output on the screen. Right. You see this here, vertical images, vertical edges. You can find it out in the Lana image, and the horizontal images you can find it in the second image. Right. Why we are getting like this? You know, because it's a summation of the neighbor, the mask is applied on every pixels. That is being summed. Right. Based on that, we are going to get these images. You can see vertical images are so clear in the first images, and similarly horizontal edges are very clear in the second image. Right. The third one, in the image segmentation concept, we have to discuss about concept called K-means algorithm, which is very well known algorithm for doing clustering. Right, the same clustering algorithm I am going to make use of for image segmentation. Right, you can see here after loading the image, just rest of the things is known to you. That's why I am not discussing about it. Here I am going to use sklearn. Sklearn is the one package used for machine learning. Right, anyway, the same package I am using here, cluster. We are going to import K-means. K-means I am going to apply. For applying K-means, I need two-dimensional array. right? Once I read the image, it is a three-dimensional array, right? So once I read the image, it is going to be a three-dimensional array. I have to make that three-dimensional array into two-dimensional array. There is a function called reshape function. With that help, I am going to make it into two-dimensional. Why? Because it's a color image. The color image means image size, and then the third coordination will be there. Three colors will be there, right? So that it is going to be done. And the values are I have to make them into 0 to 1, so that I am just dividing it by 255. Once I read the image, I have to divide it by 255 to make them into between 0 to 1. That is the first step. And then I have to reshape that. I have to reshape that into two-dimensional array. And then I am applying a k-means algorithm with the 4 number of clusters I have made it here. And the initial values of the random state is equal to 0. And then once I apply the k-means, I can able to find out every clusters on that. So how many clusters I am going to make? Only 4 clusters I am going to make. And after finding that, I am going to make a reshaping of that image into the original format, and I'm going to display that in the screen, right? You can see that original image has multiple colors. Original image has multiple colors. You can see only 4 colors in this one: green, blue, white, and gray. You can see there's only 4 colors available here in the result clustered image, right? You can see the sky, white color sky are different color, and blue skies are there. And similarly, the greenery part of this image, you can see the greenery part of the image. Some of them are trees, some of them are shadows of the tree. That is being clustered separately. That is being clustered separately. The wood part, wood of this wood colors available in the original image are like a gray level, like a gray level images, right? So this is what we have done in the image segmentation. We have segregated the image into 4 parts here. If you increase the number of clusters, you can find out every part separately. So this is what image segmentation is all about, right? And then next, color models. Color models are available in the image processing, like RGB, HSU, like CEMY and HSI, right? So like that, there are many color models available. You can see tetrahedron, right? Tetrahedron shape is available here. One tetrahedron in the top, and the bottom, the inverted one, you can see. So there is a white portion is indicated in the top, and black color is indicated in the bottom. The difference between the white and black is nothing but intensity. The joint portion of this two tetrahedron, RGB, you can see RGB here, right? So that same thing is represented, how CMYs are represented here. This is one type of representation. The other type of representation, with the help of cube, we can easily understand, right? So you can see the cube is very well differentiating these colors, right? See, black is 0, 0, 0, white is all ones, and if it is a green, 0, 1, 0. If it is a blue, 0, 0, 1. If it is a red, 1, 1, 1, 0, 0. If it is yellow, what is that yellow? 1, 1, 0. What is that yellow? Is 1, 1, 0. Like that, you can able to understand how color models are represented with the help of cube. Now you see there are different color models. I told you RGB, CMY, and similarly HSI, right? So what is the purpose of these color models now? Where it is mostly used? You can see RGB model ask what is added to the black, whereas CMY ask you to what need to be subtracted from white, means 1 minus RGB value. What is CMY? CMY is nothing but cyan, magenta, and yellow, 3 different colors, is equal to 1 minus RGB. It's a matrix manipulation. 1 minus R, 1 minus G, 1 minus B. Very simple, right? CMY can be easily found once you know RGB values of the image. You can easily convert them into the CMY. C is equal to 1 minus R, M is equal to 1 minus G, 1 minus B. Right? Where it is exactly appropriated? Absorption of colors, where we need exact values of colors, there you can use the CMY model, and which is also used in the printing of devices and such as filters, right? Used in the printing devices and as well as filters. There it is CMY model is more important. And hue, saturation, intensity, right? Hue, saturation, and intensity, HSI model. How it is computed? There is a small simple formula. Intensity is equal to RGB by 3. It's a simple average value of RGB. And what is S is all about? S is nothing but 1 minus 3 divided by RGB, R plus G plus B, minimum of RGB. minimum of RGB multiplied by minimum of RGB, right? What is that? 1 minus 3 divided by R plus G plus B into minimum of R comma G comma B, whichever is minimum among this value that we will take, and we have to summation of RGB values, and then we have to divide that 3 by that summation. And similarly, there is a formula for H value. It's a cost value, cost of manipulation with the RGB. Okay, simply we can convert from one color model to another color model. Once you know one color model, RGB model, then you can easily convert from one color model to another color model. Right. Intensity is determined by actual amount of light. Actual amount of light, and hue is determined by dominant wavelength, and saturation is determined by excitation purity and depends on the amount of white light mixed with the hue. Right, this is what we have to understand. Where this YIQ model is useful. Right, in the color television, this YIQ is used actually. Luminance, in phase, and quadrant. Right, is a recording of RGB for color television. What is the formula for this? Only a matrix multiplication. YIQ is equal to, there is a one matrix available here, and RGB. Right. What is the 3 by 3 matrix with RGB? Then only we can make the matrix multiplication. Matrix multiplication means that 0.299 into R plus 0.587 into G plus 0.011 into B. This is the first value. Second value will be 0.596 into R minus 0.275 into G minus 0.321 into B. It is nothing but I. Similarly, Q also calculated. Now you come to the next one. How to convert from one color model to another color model. Here I have taken one example to convert a HSV, right? RGB to HSV. I am just reading the image, and after that I am going to convert RGB to HSV model. This is a function calling, only a function calling. The function will does all the things. What the way we have converted in the example, with the example of the equation, same equation is applied, and we are going to get it in the image result. Right now, the first channel is nothing but a HSV. The hue is nothing but available in the first channel. Saturation is available in the second channel, and the value is available in the third channel. Right, and that way we assign the values here, and then we are going to display that in the screen of these images now. H channel, S channel, and hue, saturation, and value. Right, you see, original image is given here, in which we applied RGB to HSV, and after that we segregated each channel separately and we displayed it in the screen. We displayed it in the screen here. Original image, H channel, S channel, and V channel. Now the last part of this portion of our presentation, we came into that last part, and real-time still image capturing. You can see this my image available here. After running this program, I got this image sample. Right now, you see what is there in that. I have to use two packages. One is that import CV2. That CV2 itself having almost all the functions available. Right, CV2 has video capture. Right, function. This function requires two parameters. First one is nothing but which camera number. Maybe if you have more than one camera, the camera index we have to say, and what type of mode we have to, what API we have to choose for reading it, using it. Right. So we have just CAP is a variable name in which we have used the CV2.video capture. This is most important. Video capture is a function which is going to interact with your camera, and we have to supply two things here. One is that index of the camera. As I have only one, it is 0. If you have multiple number of cameras, you can specify the camera index 0. By default, it is 0. The 1, 2, 3. If you have 3 cameras, you can specify what camera you are going to access. Right. So 0 is here, and CV2.cap_dshow, direct show it is. Direct show API, I'm going to use it for it. Right. This is the capturing. Once you execute this capture, video capture, it is accessing the video camera. Right now, I am going to read it. Only one time I'm reading it. Cap.read, cap.read, and cap.release. Once I read it, I just released it. And the read information is available in IMG. I'm going to show it in the screen. I'm going to show it in the screen. And after that, I'm going to come out of the screen by pressing the any key, by pressing the any key. I'm just waiting for a key, and after that, if any key is pressed here, then immediately what I'm going to do here, I'm going to destroy all the windows available here. So just I'm going to come out of your application. If you press any key after executing this program, if you press any key here, it will come out of your execution. We will discuss about both execution of a video. Same functions, I'm going to use it for video capturing. Only thing is that what I'm going to do, I'm going to continuously read the frame from our camera. Continuously, I'm going to read the frame from our camera. Once it is a single reading, is going to give you only one frame. So I'm going to multiple times, I'm going to read it. Right? When I'm going to come out of this continuous looping, when I press small q, I can say I am going to come out. So in that case, I can say destroy all windows. And when I'm going to say when key is pressed, the value of q is nothing but q. Value of key is nothing but q. Then I'm going to quit out of this. I'm going to quit out of this, right? So this is what I'm going to come out. This is the way I'm going to come out of the looping statement. After coming out of the looping statement, I have to release from my capturing. Right? I'm going to release the camera. Right? Cap.release. Only simple. Initialize the capture, and after that, go on reading the camera frame every seconds. It's going to read. Right. So after reading it, what I'm going to do, I'm going to show it in the screen, and I'm going to wait for a key to be pressed. If the key is Q, then I'm going to come out of this, and I'm going to release the camera. This is a continuous phase. So once you have that in the frame, you can save that. You can save that, right? So continuously you can see that video camera is streaming, right? That is what we are going to see. For an example, I have executed this program, and I have just captured three different images from the camera, and for our demonstration purpose, you can see that, right? Now, if you have any queries, we can ask this query after the demonstration, right? Let me go to the demonstration, and then we can come back here, right? You see, currently I'm using my camera also. Let me off my camera, then I can make use of that camera for our execution. Okay, so let me stop my camera, video camera. Yes, it is stopped actually. Now I'm going to execute the camera option program. Is this here? Yeah, camera program, right? Let me execute this program. You can see there is one more window comes out of this. It's a current window. Okay, so currently I am my image is captured from my camera, and once I press the any key here, this window will be destroyed. Right, this is one demonstration. The other one is that for video, continuously it has to capture. Just I am running this. You can see my hands are moving in front of my camera, right? You can see that it is continuously reading and capturing the video frames. And if you want to save them, you can use the I am write for saving the frames frames individually, right? So even if you want to save it in the JPEG format or any format, you can use it. Right now, I have to press Q here to come out of this. Actually, I press the Q. So